Hi class, welcome to the next section, chapter 7.1. Chapter 7, we're going to focus on bridging the gap between Calculus 1 and Calculus 2. So here, I really think of chapter 7 as like an introduction into Calculus 2. Calculus 1, we focus on derivatives, we call it differential calculus. Calculus 2, we call integral calculus, where we focus on what are called integrals, which we'll get to in a couple of sections from now, right? And then calculus 3, just so that we're being thorough, is a combination of calculus 1 and calculus 2. You're really putting the ideas from calc 1 and calc 2 together in 3 dimensions, okay? So that's that's kind of the process of the calculus sequence. So for 7.1, we're going to talk about is how to approximate the area under a curve. Okay. So this is a very important idea. It probably wouldn't seem like it from the beginning, from the outside, right? Area is important to us. Area leads to volume, right? And volume is how we characterize a lot of different things. The same with area. But you wouldn't think that the area under a curve would be very important. But just like the derivative, it has more implications and applications than just finding the area from one point to another under some function, right? So again, this leads us to what's called integral calculus. So calculus 2 is primarily focused on how to find the area under a curve. Obviously it's a big study. It's a big deal because we have an entire class that's dedicated to that study, right? So far we've only been talking about differential calculus. So here we're gonna kind of bridge the gap between calc 1 and calc 2. We can think of this as like an introduction into calculus 2. This entire chapter, not just this section, right? So when we say the area under a curve, we generally are talking about, not generally, we always talk about from the x-axis up to our function. Okay, that's generally what we mean by the area under a curve. We are not just talking about all of the space under a curve. We're bounding it by two sort of points, right? Two different objects, which is the x-axis and the function itself. So we always have, not always, we generally like to talk about a starting point to an ending point, right? So maybe I would say, what's the area under the curve x squared, a parabola, from 1 to 7, right? What would be the area from 1 to 7 on the x-axis up to my function x squared, right? So here we have a curve. I know it kind of looks like a parabola, but this could be maybe sinusoidal. And I'm just showing you a portion of this curve. And so generally what happens is I want to know from some initial point to some terminal point, what is the area under this curve? Now you might look at this and say, oh, it kind of looks like a trapezoid. And it does. However, this curve here gives us a problem because it's changing over time, right? So I can try to approximate this with just a generalized geometric shape like a trapezoid. Sometimes that's very, very helpful, and sometimes it's not, because what we're going to do is we're going to create a systematic approach to finding the area under a curve using geometric shapes. And so in this case, a trapezoid would work, but a trapezoid wouldn't work every time, right? So we want to talk about how can we always generally find the area under a curve. So that's what we're going to do, is we're going to start off by approximating this area using geometric figures. Okay. So again, since the curve is always changing, it's hard to find the area below it because this is not a straight line. So I can't just say, let me use a trapezoid, right? So the easiest geometric object that we can use is a rectangle. Okay. So what we do is we just create a bunch of rectangles under our curve. Now I could try to generalize this with a single rectangle, but as you see, I get an overestimate and a pretty large overestimate as well. So the area of this rectangle is approximately equal to the area of the dark shaded region under this curve. But the approximation is not great because there is a lot extra, right? So it's not a very good approximation if I only use one rectangle. So what if instead of using one rectangle, let's say I break this down into two rectangles, okay? So instead of having the one rectangle, you can see there's a big part that is now missing. So my overestimate, right, is just this lightly shaded part and this lightly shaded part. It's a lot better than this big portion here. So creating two rectangles instead, right, where the endpoints is the height of my function, right? So I have from A to B, I cut it in half, and at the halfway mark, if you notice, the height of the first rectangle is just the height of my function. And I go over, and so I have one rectangle. It's an overestimate, but it's not terrible, right? It's not great, but it's not terrible, not like the first one was. Here, for the second half, I do the same thing at the right endpoint. I take the height of the function, and I create a rectangle, and you can see I have another overestimate. So I can kind of systemize this in order to get a good approximation or better approximation. So let's say instead of doing 4, let's say I cut each one of these in half, right? So instead of 2, now I have 4. Okay. So the more rectangles we have, the better our approximation. So let's do, so n is the number of rectangles that we have under a curve. So here, n was 1. Okay. Here, n is 2 because I have 2 rectangles. Right. So n equals 1, that's a bad approximation. N equals 2, as you can see, side by side comparison, the shaded area here for n equals 2 is much better than the shaded area here in order to try to guess what the area under this curve is. If I take each one of these in half and I get n equals 4, this is a lot less of an overestimate than this one is. Okay. And in fact, this as an approximation is way better than n equals 1. So let's say I cut these in half and I have n equals 8. Now, as you can see, I'm still over, right? There's still an error here. If I take all of the areas of these rectangles and add them all together, it very closely approximates the area under this curve. A lot better than n equals 1 does, but not perfectly, right? There's still going to be an error here, but it's not as bad if I just use one triangle or two triangles or even 4, right? So the more triangles I use, or sorry, the more rectangles I use, the better my approximation for the area under the curve is going to be. Okay. So in fact, what we do is we let n go to infinity, because as n goes to infinity, so remember what's going on here. The height of this rectangle is given by my function. So if my area under my curve has infinite rectangles, okay, so at every single point on this line is now a rectangle, n goes to infinity, that is exactly the area under my curve, right? If you think about this, if you think about just coloring the lines, if I was to color this, I could draw straight lines up and down, up and down, up and down, up and down until I color this, right? That's like an infinite number of rectangles where all of those rectangles are infinitely thin. So that's what it means to have the number of rectangles go to infinity. Okay. So we approach the exact area as n goes to infinity. So far their approximations have been right-hand approximations, because what's been going on is on the right-hand side of our rectangle, that's where we evaluate our function to give us the height of the rectangle. Right? So all of the rectangles, the heights have been given by whatever the function value is on the right side, right? So on the right side, that's the height of my rectangle. So we can also do that on the left-hand side, okay? So depending on the way that my curve is, the left-hand approximation or the right-hand approximation can either be an over-approximation or an under-approximation, right? So in this case, the right-hand approximation is an over approximation, right? It's an overestimate because everything is over. If I take it from the left side instead, everything will be an under approximation, right? So if we come here, I'll come back to this in just a second, right? So here, if I do the left-hand side, you can see that the rectangle is much smaller than the area. It's an underestimate. Okay, and so it's the same curve, right? Obviously, n equals 1 is not a very good estimate. N equals 2 is much better. As you can see, the dark shaded region is much closer to the full area under the curve. Obviously, if we have more, it will be better, right? N equals 4, you can see the error is minimized by quite a bit. And n equals 8, the estimate is much better, right? So here again, look that the left-hand side is evaluated at the function to give us the height of the rectangle, okay? So really what it is the concavity, okay? So depending on the concavity and which side of the concavity you're on will determine whether the left-hand side is an over approximation or under approximation, and if the right-hand side is a over approximation or under approximation as well. Okay, so imagine for a second that we were on the negative side of the x-axis, okay, for our a to b, and I use a left-hand approximation. So here my left-hand approximation, right? So meaning that, again, the height of the rectangle is given on the left side. So I find the height and then I move to the right until I have my next rectangle, right? So here on the right side of the y-axis, right, where we're increasing, you can see that it's an underestimate. If I did the same here, if this was the height of my rectangle and I moved over, I would have an overestimate, right? Everything would be higher. So depending on what side I'm on and the concavity, right, whether I'm decreasing with my concavity or increasing with my concavity, I'll either be an overestimate or right, or an underestimate or an overestimate, right? So here I'm concave up and increasing, so my left-hand approximation is an underestimate. When I am concave up but decreasing, my left-hand approximation is an underestimate. If we come over here to the right-hand approximations, right, the right-hand side now tells me the height. On the increasing concave up side, my right-hand side approximations are overestimates. If I was to come over here and I went up and then I moved to the left, notice that I stay under the curve. So when I am concave up and decreasing, my right-hand sums are going to be underestimates, right? And all of that changes if I'm now concave down, right? So you got to kind of think of it. It's a good idea, or it's a good practice to think about this in your mind. Well, obviously, you can always draw some pictures. I definitely like to ask questions about this. Will the right-hand sum be an overestimate or underestimate over this interval? And you have to think, well, okay, am I concave up? Am I concave down? Am I increasing? Am I decreasing? All of those play a factor into whether or not your right-hand sum is an overestimate or underestimate, or if your left-hand sum is an underestimate or overestimate. Okay, so that's really what all of this is saying. Okay, it's just saying, hey, for my right-hand approximation, since my curve is on the right side, I'm going to have an overestimate, okay, because of the concavity here. But my curve is concave up and increasing on the right-hand side, I'm going to have an overestimate for my left-hand approximation, and so forth and so forth. So basically, it's just saying that when we have concavity, our left-hand and right-hand sums are either overestimates or underestimates. And it changes depending on whether we're increasing or decreasing. So again, the concavity and whether or not we're increasing or decreasing on the interval will determine whether we're an overestimate or underestimate. Now, we are going to also run into cases where the interval over which we are estimating, our function changes, maybe has a max and min over that interval. So for part of the interval, I'm an overestimate, and for some of the interval, I'm an underestimate, right? So in total, we have to see, well, okay, my over or my under, right? So now the way that we form these approximations are called Riemann sums. So I've been talking a lot about adding things together, my summations. My sums give me an approximation, right? So right-hand approximation, left-hand approximation, those are equivalent to my right-hand sum and my left-hand sum, because I'm going to take a bunch of areas, a bunch of rectangles, take their areas and add them together. So I'm finding a sum of a lot of different things. Okay, so we call all these sums together a Riemann sum. So actually anything that follows a pattern like this is called a Riemann sum. So we're just going to generalize what a Riemann sum is first. We're going to introduce some notation so that we can learn how to work with these things. Okay, so this is the notation for a sum. Depending on your pre-calculus instruction, maybe you've seen this before, maybe you haven't. If you've taken my class before, then you've seen this. If you want to get really deep into this, or not really deep, but if you want to understand sums a little bit better, you can go through my pre-calculus material to see how to do sums and how to deal with those. There's some pretty nice little tips and tricks in there for finding areas of sums in a much easier fashion. In Calculus 2, you deal with sums a lot, okay? So like you might be like, oh, this is a lot right now, but it's better to see it now than to be introduced to it the first time in Calculus 2 when we do a very, 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 very deep dive into summations and how they work, right? So right now we're just going to scratch the surface. We're just going to talk about notation. If you ever taken a statistics course, you'll see summation notation in stats all the time. That's very, very common in statistics. Here, K is called my index counter. It's basically what happens is that we count it by ones. Okay, so K tells me all the things that have a K on it will count. C is where I start at. Okay, we call this the starting index. So maybe I say K equals 0. That means I start at 0 and then I go 0, 1, 2, 3, 4, 5, 6, so forth and so forth, all the way up until N. N is my ending index. So C is where I start, N is where I end, K just tells me all the things that change. Okay. A subscript K are the terms that we're going to add together. Okay, so this sigma notation here means I'm going to add up all of these things, all of whatever a to the k is. So here it just looks like it's a1, a2, a3 like that, but actually it really just it depends because a subscript k can be a formula. Generally it is a formula, right? So maybe this is something like 1 over k. So I'll have, in that case, counting 1 over, and my denominator would count up by k, or it would start at c and would count up by 1 until I reached n. Okay, so let's just do an example so we can really see how this works. So here we want to find the sum of 2 to the k minus k from k equals 0 all the way to k equals 4. Now notice here that this is actually 5 things that will add together because I start at 0 and then 1, 2, 3, 4. That's 5 elements. Okay, so I start off with 0, meaning the first thing that I'm going to have, the first item, the first object, the first term is me plugging in 0 everywhere for k. Okay, so I'm going to take this. The first one I'm going to have is plugging in 0 everywhere for k. Okay, so k counts starts with 0. I'm going to add to that. I've already used the zeros, so now for the next one, I'm going to plug in 1 everywhere for k. 2 to the 1 minus 1. On the next term, I'm going to plug in 2 everywhere for k, right? 0, 1, 2. This will be 3, and then 4, right? So that gives me 1, 2, 3, 4, 5 things to add together, just like we said. So I started at 0 for my values of k, and I end at 4 for my values of k. And I count up by 1 everywhere I see k. I plug in 0, and then 1 more, and then 1 more, and then 1 more, and then 1 more, until I get to my ending index. Now, it's not enough to just to have this. I have to actually add them together, right? So 2 to the 0 is just a 1. I'm going to subtract nothing. 2 to the 1 is 2, minus 1 is 1. This is 4 minus 2, so 2. 8 minus 3 is 5, and 16 minus 4 is 12. Now I actually add these together, right? So I got 1, 2, 4, 9, and 21. Okay, so one thing that's neat about summations is that we can change the starting index and the ending index if we change this a subscript k term, and we can have the exact same summation, right? So here, let's say that we change our starting to be 1, okay? So if I change my start index to be 1, then my ending index has to change by 1 also. So I go, instead of from 0 to 4, I'll go from 1 to 5. So since I'm starting at 1 later, all my values of k should be 1 smaller, right? Because here I plug in 0, I get out 2 to the 0 minus 0. So if I take all my k's and subtract them by 1, since I'm starting at 1 later, look what happens when I plug in 1. I get 2 raised to the 1 minus 1, 0, minus 1 minus 1, 0. I get the exact same thing for my first value. I'm still separated by 5 values because I have 1, then 2, 3, 4, and then 5. So that's still 5 values, right? So I still have the same number of values as I did before. My first term agrees. Okay. So here I just simplified, I distributed this negative value. So this will give me the same output as this example I have here. If I simplify this a subscript k that I have, right, this whole equation, I can distribute this negative sign, and I have a third form that's equivalent that gives me all of the same values, right? So again, if I plug in 1, I get 2 to the 0 minus 0, right? When I plug in 2, I'll have 2 minus 1, which is 2 to the 1, and I'll have negative 2 plus 1, which is negative 1. When I go to the next one, 3, I'll get the same thing. When I plug in 4 here, I'll get the same thing, and when I plug in 5 here, I'll get the same thing. So all of these 3 are equal to the same value. It's all the same sum. Okay, so let's combine everything together. This idea of having a Riemann sum, my Riemann sum really being a bunch of rectangles, okay? My rectangles are going to be evaluated either on the right-hand side of the rectangle or on the left-hand side of the rectangle, whichever one. The height will be given by the function, right? So either my left-hand side is how I'll talk about how tall my rectangle is, or the right-hand side of my rectangle is how I'll determine how tall my rectangle is. It really just depends on what I ask you for. If I say give me a right-hand sum or a left-hand sum, that's the difference, okay? Notice that I like to have my rectangles when I have more than one. It's not necessary, but it's preferable to have them have the same base size, right? So here, the size of this single base is b minus a, right? The size of this is b minus a, the difference, divided by 2. Here, each rectangle is b minus a, the length between a and b, divided by 4, right? 4 equal parts. Here is b minus a divided by 8. 8 equal parts. It's much easier if they're equal in length, right? Because then that tells me it's very methodical, it's systematic. If I did it all willy-nilly, there's not really any formulas I can develop for that, right? So it's much easier if I can develop some sort of formula. So uniformity is definitely preferable. So coming over here, again, putting these things together, we're going to form a sum of rectangle areas, okay? The size of each of those bases is the difference between the length of the interval that I'm interested in, b minus a, divided by n, however many rectangles it is that I want, right? So again, if I want one rectangle, it's just b minus a. If I want 2 rectangles, it's the distance between a and b divided in half. If I want 12 rectangles, it's the distance between a and b divided by 12, right? Divided into 12 equal parts. So that's the size of the base, okay? That's the distance between each x value that I'm going to look at, right? So every time I move over a distance of b minus a over n, I have to plug that value into my function so that I can find how tall my rectangle needs to be, right? So I plug in a value, I get the height of my rectangle. I know the base, right? It's b minus a divided by, in this case, 2. So that's the area of one rectangle. I come to the next rectangle. It's a distance of b minus a over 2. That's the distance to the next point that I'm interested in. Plug that into my function, and now I have the height, and I can multiply that times the length, which is b minus a over 2 in this case. Okay, so this is the length between each of my x values because I want it divided into n equal parts. Okay, so we will call that the change in x, delta x, right? The distance between each x value is the change in x. So b minus a divided by n is the length of each of those bases, right? So if I'm going from a to b, if I divide it into however many parts, I know here it's 8 parts, but it could be 100 in this case. The length of just one rectangle, one base, that is delta x. That is a length of b minus a over n. So we actually now have n plus 1 x values that are interested to us because I have a and then all the n points in between until the end, right? So I divided these into n pieces. So in this case, 8, right? Actually, let's go to one that's easier. Let's go to this 2 again. Okay. Here I have one rectangle, 2 points of interest. Okay. 2 x values. Here I divide into 2 pieces, right? N equals 2, but there are 1, 2, 3 x values, right? Here there is 4 rectangles, but there's 1, 2, 3, 4, and 5 x values that are interested in me. The first one, the last one, and then the ones in the middle. Oops. Okay. So I have n plus 1 x values, right? So if I divide it into n pieces, I have 1 more x value than the number of pieces I divided it into. So I have x naught, right? My first x value, which is my starting value of a, the first part of my interval. And then my next x value is my previous x value plus that change in x, okay? My next x value is my previous x value plus the change in x, and so forth until I get to my last set of values. Okay, so I have n, so from a to b. Now, if I form a right-hand sum, I do not evaluate at x naught. So that eliminates one of the values that I have x value-wise of interest to me, and that leaves me with n things to plug in. Okay, so again, let's come back here. When n equals 2, I only evaluate at 1, 2 of those places. One of those places will be left over. This is for the left-hand sum, right? So when I'm on the right-hand sum, okay, I evaluate not at a, so not at the first one, not at x naught, but at x1. I evaluate, and then at x2, or in this case xn, I evaluate as well to get the heights. Okay, so that means that one of my x values I didn't use at all, right? All right. So if we form the right-hand sum, or RHS as we like to call it for short term, then I start with the x1, not x naught. I started at x1. I don't evaluate a at all, right? So my first height for my first rectangle is the second x value, right? x1 being plugged into my function, and then f of x2, and so forth until I get to the last one, right? So right-hand sum, it's always the last value is the last one that you should plug in. Okay, you know, left-hand sum, it's completely opposite. I start with my first one, right? So first one, and the last one never gets evaluated. All right, try not to go backwards anymore. So if we have a left-hand sum or LHS, then I start at x naught and I go all the way into the one just before the last x value. Okay, so that gives me n for both of these. So either I'm using the first one or I'm not, or I'm using the last one or I'm not. So that's always the case, depending on if I'm a right-hand sum or left-hand sum. The ith rectangle, so really just any random rectangle in the middle is what we mean by the ith rectangle. In a right-hand sum, we'll have an area of f of xi delta x, because the first one that I evaluate for the first rectangle is f of x1. The x value I use for the second rectangle is f of x2, and so forth and so forth. So the ith rectangle in the right-hand sum is just x sub I. So the seventh rectangle will have a height of f of x7 times delta x. The ith rectangle in the left-hand side has an area of xi minus 1. Okay, because I'm starting at the zero term, the first term, the initial term. So, for instance, in the left-hand sum, the seventh rectangle will have a height of f of x to the of x6, right? The sixth x value is what will be plugged in. So, if we summarize this, I got A to B. Here I have delta x. For the ith rectangle, this is xi, gets plugged in if it's a right-hand sum. If it's a left-hand sum, I would use xi minus 1. So if this is what, 1, 2, 3, 4, 5. This is the fifth rectangle. So if a right-hand sum, this would be x5, which it is, right? 0, 1, 2, 3, 4, 5. If I was using a left-hand sum, I would be plugging in x4 instead of x5. Okay. So in order to form a right-hand sum, again, I'm looking at all the right-hand sides. So x1, x2, x3, x4, x5, all the way up to b. It's approximately going to be the height here, which is my function value, times the base, right? Every area is base times height. So the height is the function being evaluated at that point, x sub I, and the base delta x. Again, that's where we get here. So for a generalized rectangle, you have your height times your base. On the left-hand side, you have your height times your base for an area. So we're going to add all of those together. So for the first rectangle, area of the second rectangle, plus all the other areas until I get to a generalized middle rectangle all the way to the last rectangle, right? So again, right now we're only going to focus on the right-hand side summations, the right-hand summations. Okay, so we're adding up all of these areas. So this can be kind of tedious, so let's see if we can try to simplify this a little bit. So notice that every single one of these is being multiplied times delta x. Right, the change in x. That is a common factor because they all have the same base, right? Which is what we did intentionally to make it a little bit easier for us. So what we can do is we can pull out this factor of delta x to make things a little bit nicer. Okay, so now we just have the sum of my function values, which we can, to make the formula a little bit nicer, we can write as a summation, right? So if you notice that what's going on is that the index counter is going up by 1 each time, 1, 2, 3, 4, blah, 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 all the way to n. Okay, so I would start at 1 and I would end at n. And I have whatever it is that my function is, right? I don't know what this curve is given by, but they're all being plugged into the same value. Okay, so delta x we know is b minus a over n. So we can rewrite our formula in this form to keep it a little bit more exact. So I start at 1 and I end at n. This is for right-hand sums, because remember, the first one I plug in is not x0, but x1 for the right-hand side. Okay. Now if I do the same sort of justification for the left-hand sum, okay, so the right-hand sum looks like this. So if you notice this common factor of delta x, I don't write it as b minus a over n. Just have to know that that's how it's formed, but we keep it here with the summation notation. However, when you're calculating it, it's pretty nice to just pull it out as a factor and just find your sums. Okay, so we're going to kind of use all the little things that are going on in here, but formula-wise, this is how we write the formula for the right-hand sum. The left-hand sum is the same exact formula, but notice the difference. I start at 0 and I end 1 less, because here, right-hand sum, I start at the first one and I go to the last term, n. The left-hand sum, I would start at a, which is x naught, and I would end 1 before the last x value I had. So I still have n x values, right? There's still n of them, but this one starts at 1 and goes to n. This one starts at 0 and ends 1 beforehand. So make sure you're paying attention to the notation, to the counters, so you know if you're doing a right-hand sum or a left-hand sum. However, the formula inside of the summation notation is exactly the same. Okay, so the larger we go, right, the more n's we have. Again, our approximation becomes the actual curve. So the actual area is the limit of either one of these. It doesn't matter. If you notice, I did use the one for the right-hand sum, but I could have just as easily wrote for the left-hand sum. I take this and I take the limit as n goes to infinity. Okay, so the more values I have for n, the better my approximation. If I let n become infinity, then I get the actual area under the curve. So we would find the sum and we take the limit of it as n goes to infinity, right? Which is equal to me taking the limit as n goes to infinity of the left-hand sum as well. They're all going to be the exact area if I take the limit. Okay, so the area under the curve tells us the distance traveled from point A to point B if our function is a velocity function, right? So let's talk about what that means. Okay, so if my function is a velocity function and A and B represent different times, right? So let's say that A is time equals 0 and B is time equals 10 minutes. My function is velocity. I should be able to tell how far I've gone in 10 minutes if I know my velocity. Now, if my velocity is constant, right, I'm always going 10 miles an hour, and I do that for an hour, I know I've gone 10 miles, right? However, in this class, calculus, right, we like to talk about functions that are continuous, that are changing over time. So if I'm speeding up and slowing down and speeding up and slowing down over time for an hour, I should still be able to tell how far I've gone in an hour if I have an actual function. And I can't do that by just saying, oh, well, I was going 10 miles an hour the whole time, but I wasn't, because maybe at some points I was going 50 miles an hour, some points I was going 2 miles an hour, that my speed was changing over time, which it does. I should still be able to talk about how far I've traveled. And that's what this does. The area under the curve allows us to talk about how far we've gone from point A to point B, or from time A to time B. Okay, so let's do an example. So let's estimate the area under the curve. F of x equals 3 sine of x over the interval from 0 to pi using a right-hand sum with 4 approximations, 4 rectangles. Okay, so it's always great to draw a picture, although you do not have to draw a picture for these, right? We have a formula that we can follow. Obviously, a picture will look something like this, right? In this case, it'll be a right-hand sum, so we'll go all the way to the right-hand sums, and it'll be 4. It'll be something like this, but it'll be a sine curve, right? Obviously, this could still be a sine curve depending on how it goes, but sine curve we know starts at 0, right? But it'll look something like this, okay? Let's come all the way back. All right, here we go, okay? So, following the formula, okay, we can't find the limit. We're estimating the area. We're not finding the exact area. We're not there yet. We'll talk about this more in the next section. But for 3 sine of x, we're from 0 to pi. So we need to divide this interval into 4 equal parts. So b minus a divided by 4. Okay. delta x, remember, is b minus a. That's the length and the number of rectangles that we want. So b minus a over 4 is going to be pi over 4. So each of our rectangles has a base of pi over 4. Okay, so delta x is pi over 4. That's the length, that's the base length of each rectangle. I always like to find my x values. I know I'm not using 0 because this is a right-hand sum, so I don't use the first one. So the first one I am going to use is a distance of pi over 4 away from 0. So my first point will be pi over 4. My next point will be pi over 4 away from pi over 4, or 2 pi over 4, or pi over 2. Okay. Another pi over 4 away is 3 pi over 4. And then the last value, another pi over 4 away, is going to be at pi. So these are my 4 x values. It's always nice to have your x values. So I always do these two things first. I always find the base of each rectangle, the delta x, the length. 1, I'm going to need it in my formula. 2, it also tells me how to find all of my x values, right? So if I'm a right-hand sum, I don't start at 0, or I don't start at this point, and then I find my next ones. If it's a left-hand sum, I start at 0, and then I find all my next points. So I have all my points that I'm interested in. So following this formula for the right-hand sum, I'm going to take pi over 4, I'm going to plug it into my formula, which is 3 sine of x, and I'll multiply that times delta x, or pi over 4, and then I'll do that with the next, and the next, and the next. So I'm just going to follow the summation notation. So my sum, starting at 1, going to n, I know n for me is 4, right? My function is 3 sine x, and I know delta x is pi over 4. So I can start to just plug those things in. I'm going to have f of pi over 4 times pi over 4. I'm going to add to that pi over 2 plugged into my function, plus pi over 4, then 3 pi over 4, and then pi, right? So this is what my notation looks like, right? This is what it looks like, but I have to actually plug this into my function. I can pull out a factor of pi over 4, pi over 4 into my function, plus pi over 2 into my function, plus 3 pi over 4 plugged into my function, plus pi in my function, right? So now I just evaluate all of these sine values. Okay, so I have pi over 4, root 2 over 2. This is going to be 1. This one is going to be root 2 over 2 as well. And then this is going to be 0. Okay. Then we can simplify that by pulling out all of the 3's. Root 2 over 2 and root 2 over 2 added together is just a root 2. This leaves me with the 1. The 3 is on the outside. So this would be the exact value for the approximation, but this is an approximation. I don't really need an exact value. So it's okay to provide decimals here for these approximations. An approximation is just that, it's an approximation. However, for now, let's just go ahead with the exact values in the future. We want to get in the habit of using exact values because when we start to take the limits, we're going to need these, right? But let's go ahead and find out what this approximation is. It's approximately 5.688356694. So having the exact value allows me to round at any point that I want, right? Which goes along with that, keep everything exact as long as possible, and then provide your decimal approximation at the last step, right? So if I wanted to compare this to the exact value, I could at this point, or I'm sorry, in the next video we can, when we learn how to find these values exactly.